All right, yeah. Thank you very much. So, before I start, I should take the opportunity to thank the organizers for this wonderful conference. So maybe we should give a round of applause to the organizers. And then, yeah, so for the last talk, what I want to give here is I want to give you some kind of a status report towards this long-term goal of eventually maybe coming up with a theory of Ricci flow in dimension 4. I'll structure my talk as follows. Oh, I should say part of this talk is joint work with Eric Chen, who was a postdoc at UC Berkeley last year. The structure of my talk will be as follows. So first of all, I want to give you a bit of a background in Ricci flow, just the bare minimum. I'll want to talk a little bit about Ricci flow with surgery, like what has been done by Perelman, and Ricci flow through singularities, all these things that have been done in dimension 3. And then I want to focus on dimension 4. I want to discuss recent results of myself on characterizing singularity formation in dimension 4. And then towards the end of the talk, I want to talk about some even more recent work of myself joined with Eric Chen, where we discuss the resolution of conical singularities. And so this will hopefully make sense when we'll get there. Okay? Yeah, please interrupt me if you have any questions. Sorry if some of these things are a bit too analytic. Okay? Okay, so first of all, let's start out easy and give some background on Ricci flow. So Ricci flow is just given by a smooth family of Riemannian metrics parameterized by some time parameter. And it satisfies this Ricci flow equation up here, that the metric evolves according to -2 times its Ricci curvature. And this is often coupled with an initial value condition where we prescribe the metric at time 0. And so roughly speaking, just roughly why this is an interesting equation is that if we write it down in good coordinates, then this looks roughly like a heat equation. So we somehow hope that as we move forward in time, the metric or the metric coefficient somehow, kind of improve, like the geometry improves in a certain sense. The most basic examples of a Ricci flow that we can actually write down are examples where we start with a manifold that's already Einstein. And in these cases, it just depends on the value of the Einstein constant what happens. Okay, so the metric will always rescale, but depending on the sign of the Einstein constant, the metric either scales down until somehow the diameter goes to 0, and this is where kind of the flow incurs a singularity. If it's 0, then of course the flow is constant, and if it's negative, then the flow wants to expand. Okay, so these are kind of the three most basic cases of a Ricci flow. Okay. But of course, these are not the very interesting cases because we want to improve a metric via the Ricci flow, and these are already perfect kind of optimal metrics. And so now it turns out if we want to study the evolution of more complicated metrics under the Ricci flow, this is often very hard to control, and in particular, the flow will often incur singularities even after some very short time. And so a key kind of goal in the field is to understand the formation of singularities when they occur. Okay? And so maybe the most famous example of a singularity is this famous neck pinch. Okay, so this is something that will show up later. So let me just discuss this here. So here in this example, I'm going to look at a rotationally symmetric manifold, maybe S3. And it's equipped with this metric that looks like a round sphere on one side, a round sphere on another side of radius R1 and R2. And they're connected by a neck of width approximately R2. Okay? So what we can prove in this case is, and that's been known for quite a while, is that the flow starting from such a metric will always incur a singularity. However, the type of singularity that we will see depends on the choice of those radii. So for example, if those radii are somehow comparable to one another, so if the neck is not very pronounced, then kind of the concavity of the neck that has some negative curvature will cause the neck to expand and somehow dissolve until the flow becomes more and more round, but since it has positive curvature, it keeps shrinking and shrinking, but as you kind of zoom in, it becomes more and more round. Okay, so if you kind of keep zooming in, then at a very small scale, the flow looks just like a round sphere that shrinks to a point. Okay, so the green thing is the kind of the model for the singularity, or we call it the singularity model. Then in the other extreme case is the case where we choose the neck very thin. And now the curvature of the cross-section dominates. The curvature of the cross-section is positive, so it's somehow more positive than the concavity of the neck. And this will now cause the neck to contract rather than expand. And this will call, in fact, the contraction here happens within finite time. So the neck contracts here, but the singularity that we see here is only local. So in fact, kind of the metric kind of remains smooth up until the singular time outside of this neck pinch. Okay? And so again, if we zoom into the singularity, then kind of our singularity model will just be a round shrinking cylinder. The S2 factor will shrink to 0, while the R factor will remain constant. Okay? And then there's this intermediate case. It won't be super important for us where kind of two of these processes happen at the same time. And then we only have the singularity here in the tip. And the singularity model is this paraboloid. And the name is a Bryan soliton. Okay, so it's not super important here right now. Okay, so this is what happens in the rotationally symmetric case. But we would like to understand the singularity formation in the general case when we don't have rotational symmetry. Okay? And so to do this, I want to make this a bit more clear what we mean by a singularity being modeled by a singularity model. Okay? So this is going to show up a bit later in the talk, so I just want to make it more precise. Okay? But this is, of course, a standard technique in geometric analysis. Okay? So singularities are often just analyzed by what is called a blow-up procedure. And the way I want to set this up is as follows. So suppose we have a Ricci flow, and I'm going to draw the space-time picture here. So the x-axis is the manifold, and the y-axis is time. And the dashed line at time t means that we have a singularity at time t. So now if we have a singularity, that means that we can find a sequence of points in space-time, so xi and ti, along which the curvature goes to infinity. Okay? So in this case, we say that the sequence of points somehow goes into the singularity. Okay? And so now we would like to understand what's somehow responsible for the singularity formation. What does the geometry near these points look like? And so to do this, we are going to choose a sequence of rescaling factors, lambda I going to infinity. And then we are going to take the entire Ricci flow, and we're going to rescale distances by lambda I, so the metric by lambda I squared, and times by lambda I squared. So that preserves the Ricci flow equation. And we're also going to center the time ti to be the time t0. Okay, so we're going to shift the flow so that time ti is t0, and then we're going to kind of blow up the entire flow. We rescale it. Okay? And so in doing so, we're going to construct a sequence of Ricci flows that somehow exist on larger and larger backwards time intervals. Okay? And then we can hope that maybe after passing to some kind of subsequence or applying some compactness theory, we can pass to a limit, and in the limit we will then get a Ricci flow that's defined for all non-positive times. And we will refer to this limit as a singularity model or a blow-up model. Okay? So the upshot here is that this process, this blow-up analysis, allows us to reduce the study of the singularity formation to the classification of possible singularity models. And now I can say what kind of Perelman's big breakthrough was in dimension 3, which was that he could classify all possible singularity models in dimension 3. Okay? And it turns out they're exactly the 3 singularity models that we've seen in the rotationally symmetric case. So that already kind of entails all the cases that happen in the general case. Okay? So the possible singularity models are spheres, okay, or quotients of it, cylinders, or the Z2 quotient of it, or the Bryan soliton. Okay, so this paraboloid. Okay? And this in the last case, Perelman only obtained something qualitative, so Bamler somehow finished that case. All right, so now we have a pretty good understanding of kind of the local geometry near these points xi, ti, as we're getting close to a singularity. So if the flow becomes very singular, then there's going to be a region that becomes very singular. And by this classification, we know that these almost singular regions need to look either very cylindrical, very spherical, or very, very kind of Bryan soliton-like. And this this realization then led Perelman to produce what is called a Ricci flow with surgery. Okay? So Ricci flow with surgery is just a sequence of Ricci flows that are parameterized by consecutive time intervals and that are defined on manifolds of possibly different topology, but the different Ricci flows are related by what's known as a surgery procedure, where we kind of remove singular regions. Okay? So the precise definition of the surgery procedure is quite technical. It takes about a page. So instead of kind of showing you what the definition is, let me just show you a little movie, and I'm pretty sure you know what this would look like. Okay? So here in this movie, I'm going to start with some initial condition. some Riemannian, three-dimensional Riemannian manifold, a closed, let's just say. Then we evolve it by the Ricci flow, and let's just evolve it for as long as we can, or maybe let's just stop like a millisecond before the first singular time, okay? And so we see these kind of almost singular regions arising, and we know by the previous analysis that they were kind of looked very cylindrical. So maybe we see this very cylindrical region here. So there's maybe these like cross-sectional S2s of some kind of very small radius delta. And then what we can do is we can cut along these cross-sectional S2s, throw away this singular kind of neck, and attach little caps to the cutting surfaces. And in doing so, well, we've changed the topology in a controlled way, but we've also made the manifold less singular, and this now allows us to run the flow again until we hit another singularity. Okay? So here maybe we have a spherical singularity this time. In this case, we just say that the flow has done its job and we just discard it. And then we maybe see another neck pinch singularity, we do another surgery, and so on. Okay? And so Perelman, of course, this is a very subtle construction, and Perelman was able to show that this can somehow be carried out for as long as we want. Okay, and I'm sure you're aware that this was somehow used to prove the Poincaré conjecture and the geometrization conjecture. So this was a very powerful flow. Okay, however, I would argue that this flow has a drawback, and even Perelman recognized this. And the drawback is that the surgery construction depends on a lot of auxiliary parameters for which there's just no canonical choice. Okay, so for example, you have to choose the scale delta at which you perform the surgery, and delta has to be positive and small. Okay, so there's no canonical number that's positive and small. Okay, so there are different ways how to perform the surgeries and different types of flows. Okay? And so even Perelman recognized this in both of his papers. So here probably he wrote, it is likely that one would get a canonically defined Ricci flow through singularities, but at the moment I don't have a proof of this. Okay, so a while ago, in work of Kleiner and Lott and Kleiner and myself, we finally answered Perelman's question. And so let me just write down the results here. So we showed that there is some kind of singular Ricci flow. So first of all, Kleiner and Lott showed that there is some kind of singular Ricci flow starting from any initial condition. Okay? And then I showed with Bruce that this flow depends uniquely on its initial data. So what is the singular Ricci flow? Well, the singular Ricci flow can be thought of as some kind of four-dimensional space-time manifold, okay? And it's equipped with some smooth structure. So for example, a time function whose level sets are kind of the time slices, a vector field whose trajectories correspond to kind of static points, and then of course a metric, okay? And so locally, this flow locally, we have somehow the Ricci flow equation, so the flow is described by the Ricci flow equation, but somehow the entire manifold may have some non-trivial topology globally, okay? This is kind of the idea. And so then what you could, for example, see here is you could see, like, look at the level sets of the time function. You could maybe see these kind of cylindrical neck pinches arising, and then you kind of flow through these singularities. So they become singular and then they immediately resolve. So essentially the surgery is somehow performed automatically at scale 0. Okay, so think of like level sets in Morse theory, for example, but it's not quite exactly the same thing. And maybe just as a side note, this flow is completely smooth because it's called a singular flow, but kind of the data that describes this flow is just smooth data because we're not kind of looking at the singular points of the flow. We're essentially just describing the regular part of the flow, and that somehow seems to be enough. That kind of also characterizes what the singular part looks like. Okay, and then just, again, as a side note, this flow had some other applications, topological applications. For example, we proved the generalized Smale conjecture and a statement about the space of positive PSC metrics. Okay? In any case, so this, in my opinion, now somehow provides a pretty satisfactory picture of Ricci flow in dimension 3. So what I want to do now is I want to continue to dimension 4.
So this space is smooth, but it's not complete, right? Basically, you are
Correct. It's not complete, but somehow you can always get the whole flow by just taking the completion. And since we have uniqueness, we know that the kind of the regular part fully describes the flow. Yeah. So in particular, we don't need to actually characterize what the equation is like on the singular part. Yeah. Good point. Okay. So let me move to dimension 4. Okay, and so here we really have to start in the beginning. So so up until recently, there was the only thing that we knew about Ricci flow in dimension 4 was in very special cases. Okay, so for example, in the case of Keller Ricci flow, or in the case where we had certain pretty strong positive curvature conditions. But for general Ricci flows, there was hardly anything that was known. So we really have to start from the beginning, and we have to ask ourselves again, what do singularities of Ricci flow look like in higher dimensions? Okay. And so just so we can manage our expectations, let me just show you a few examples of what could happen in higher dimensions, what does not happen in dimension 3. And so to illustrate this, let me show you an example of a graduate student of mine, Alexander Appleton, who constructed very special Ricci flows in dimension 4. They had like a lot of symmetries, but it was like a 100-page paper with lots of computations. So he constructed these Ricci flows in dimension 4 whose singularity models he could classify. Okay? And so the singularity models are the following. They're either the Iguchi-Hansen metric, or R4 mod Z2, or the Bryan soliton mod Z2, so that you have like an orbifold singularity at the origin, or the cylinder or the quotient RP3 cross R. Okay? So depending on how you kind of choose your rescaling factors and your base point in the blow-up analysis, you see one of these 4 singularity models. Okay? So just to review what they are, so these 2 singularity models are Ricci flat. So Iguchi-Hansen is Ricci flat and asymptotically locally Euclidean. So it's asymptotic to this cone, R4 mod Z2, so that's cone over RP3. And then, of course, the Bryan soliton mod Z2 has an orbifold singularity, so these are singular. And the singularity is exactly that R4 mod Z2 singularity. And then again, the Bryan soliton mod Z2 is asymptotic to the cylinder with the RP3 cross-section. Mm-hmm.
What do the brackets mean?
Oh yeah, so I wanted to get to this. So in his analysis, there were 2 possible behaviors of the flow. And we still don't know which of these 2 behaviors occurs. And so depending on which behavior occurs, we either only see the first 2 singularities or we see all 4. Yeah, but yeah, good point.
And the point is to design the initial condition that you convert to one of these 4. So what is it?
So yeah, so you design the initial condition and you have a flow that becomes singular. There are 2 different kind of ways how the singularity could form. And depending on what happens, you see either, and then take one of these flows and then you can choose rescaling factors. If you kind of look at the lowest scale, you see the Iguchi-Hansen metric. If you see at the next scale, you see this R4 mod Z2. And then now, depending on which flow you are, if you look at the next scale, you might see the Bryan soliton in the cylinder. Yeah, so I can draw this later if you want to. Okay. And then let me also point out, and we'll get to this in a moment, there are 2 singularity models which are called gradient shrinking solitons. I'll define this later, but they are somehow very good singularity models. This is kind of what we're going to be looking for. Okay, so so don't worry about the name here. But my point here is that it may happen that we see these somehow good singularity models, but these singularity models are singular themselves. Okay, so this is somehow the new thing that happens here. In dimension 3, the singularity models, they modeled a singularity, but they themselves were not singular. So now certain singularity models that we want to look at may be singular. Okay? And then this idea was also reinforced by Stolarski, who showed that there are similar Ricci flows in higher dimensions that have to develop singularities, and then the only kind of gradient shrinking solitons that we see are singular themselves. Okay? And then there are kind of similar results in Keller geometry. Okay? Okay, so let me just make the conclusion here. This is all I want to say here, is that if you want to study singularity formation and blow-up analysis in higher dimensional Ricci flows, we have to allow singular singularity models. Okay? And so we have to find a process how we understand singular Ricci flows and how we understand convergence towards singular Ricci flows. And this is what I came up with a few years ago. So a few years ago, I came up with this theory, which is like a compactness and partial regularity for Ricci flows that allows us to study singular Ricci limits of Ricci flows. Okay, so let me just in the slide present a bit what this theory tells us. And to kind of introduce this, let me just start with this blow-up procedure that I showed on the previous slide. Okay, so again, we have these rescalings here, these parabolic rescalings where we kind of zoom into the singularity, and then we see this singularity model. Okay? But now the problem is the singularity model may be singular. Okay, so what we need in this new theory is now the following. So we need a notion of some kind of singular Ricci flow, okay? So some kind of maybe synthetic Ricci flow that is allowed to have singularities. And by this I don't only mean a Ricci flow in a singular space. I want to allow singularities to move around in time and the structure of the singular set to change in time and maybe even the topology of the time slices to change in time, okay? So this has to be kind of singular in space-time. Okay, and so this is what I answered in this work. So I came up with this new notion of what is called a metric flow. Okay, so think of this as kind of a family of metric spaces and some kind of parabolic analog. Okay, there are certain axioms that they have to fulfill and so on. And in my opinion, this is the right notion to look at. Okay, so the limit here should be a metric flow. But then we also need a different topology within which this convergence happens, because we don't have smooth convergence anymore because the limit is not smooth. And this is another definition that I made. So this is, I call this F convergence, okay? Think of this as some kind of parabolic analog of kind of Gromov-Hausdorff convergence or measured Gromov-Hausdorff convergence. And then, well, then we have this limit, which is a singularity model, but this may be just like a very wild space, so we also need some kind of partial regularity theory, okay? So we need to say that this limiting object is actually not as singular as we were we worried it would be. Okay? And so this is really kind of the main part of this theory. And just to kind of illustrate this, like, let me just give you like a very basic statement of the theory. So it says the following. It says that, just like with many of these geometric equations, that this limiting Ricci flow has a decomposition into a regular part and a singular part. And, well, the singular part has codimension 4, at least 4, in space-time. So we have to assign 2 points to the time direction, but then it's codimension 4. And then the flow on the regular part is given by some kind of smooth Ricci flow space-time structure, just as what we've seen before, okay? So locally, the smooth Ricci flow equation holds. And in fact, the regular part, again, just determines the entire flow. So it's actually enough to just look at the regular part and forget about all the other stuff, okay? You see, are there any questions? Mm-hmm.
Why is time two-dimensional? Why relating to?
And that's how it scales. So distances have dimension m meters, and time has dimension square meters. Yeah. All right. Okay. So now we have this new theory that allows us to extract a singularity model from a Ricci flow that becomes singular. But now we have the singularity model. So what do we do with the singularity model? It's just some ancient flow that exists for all negative times. How do we analyze the singularity model? And well, there's kind of a standard trick, and the standard trick is also allowed in this theory, which is that we're now going to take this flow and blow it down. Okay, so we're going to take this singularity model, which exists for all negative times, and then we're going to parabolically rescale it down. So we're going to multiply distances and times with factors that go to 0. Okay? So when we do this, then we're essentially going to look at the behavior of the flow as we go to time minus infinity. Okay? Because times that are very close to minus infinity are now going to be shifted very close to time 0. Okay? So we're now going to take these blow downs of the flow, and then what we get in the end, and then we can apply this compactness theory again. So we get some other metric flow in the limit, which again has a regular singularity composition. And then what we can show is that this limit is what is called a gradient shrinking soliton. Okay, so what's a gradient shrinking soliton? Well, a gradient shrinking soliton is a Ricci flow where in every time slice, or sorry, I forgot a factor of tau, where at least in one time slice or in every time slice, an equation like this is true. Okay, so this is something like the Ricci, like the Einstein equation with a positive Einstein constant, but there's this extra Hessian term in there. Okay, so examples of gradient shrinking solitons are, for example, the round sphere or the round cylinder. Okay, so these are all solutions to Ricci flows that are self-similar. So they all, if you evolve the sphere by the Ricci flow, then it will just rescale. And also, if you evolve the cylinder by a Ricci flow, it will rescale modulo diffeomorphisms. Okay, at least in its isometry class, it will just evolve modulo rescaling. And gradient shrinking solitons are exactly those flows that evolve by rescaling. Okay. And so now this reduces since this kind of limiting flow is self-similar, this now reduces the study of the entire flow to just the study of one time slice. which satisfies this nice Einstein type equation, and then you can somehow say more about the singularity model, like its structure at infinity and so on. Okay, and so so in dimension 4, this flow is even like a smooth orbifold, or this soliton is a smooth 4-dimensional orbifold. Okay, so this is kind of this theory, at least in a nutshell, but let me just show you 2 consequences of this theory to show you kind of that this is hopefully useful in the study of Ricci flow. And so the first consequence of this theory is a way of kind of characterizing, it's like a first kind of characterization of singularity formation of general Ricci flows in dimension 4. So up until now, there's nothing that's known. Now we know a little bit more. Okay, so here's the corollary. It says the following. It says, suppose that we have a 4-dimensional Ricci flow that becomes singular at some time, capital T. And then, well, either if we rescale the flow appropriately, so this rescaling here is kind of the right one, then we just converge to a gradient shrinking soliton. We maybe converge to a round sphere, or say maybe some slightly more complicated soliton. So this is what we always have to expect, that something like this could happen. So we're just asymptotic to a soliton. However, if this does not happen, so this is somehow the bad case, then one of the following is true. Then the following is true. And then we can find a sequence of base points and a sequence of rescaling factors, such that if we take blow-ups along the sequence with these base points and rescaling factors, then we see one of the following singularity models. So we again either see a cylinder, we just have to allow quotients of the cross-section this time, or we see a 2-dimensional cylinder, so where the cross-section is as 2 cross R2, or, and so this is kind of especially new here, a smooth Riemannian cone with positive scalar curvature. Okay? So this is somehow what we see. So this is what the theory says. So either we're in the good case and we just converge to a gradient shrinking soliton. This is what we kind of would like to see. Or we're in the bad case where kind of maybe part of the flow becomes singular and the other part doesn't become singular. But at least then we see these regions that look either cylindrical or conical. And these are kind of the regions where we want to perform surgery in the end. Okay? There's a more general theory for this, but this is maybe the kind of the most illustrative corollary here. And then maybe just as a side note, let me not dwell on this. So this theory also had some application in the construction of gradient shrinking solitons. So there's a paper with Cifarelli, Conlon, and Derwell, where we actually turned the story around. We used this theory to kind of write down a Ricci flow that we knew had to become singular, but we knew that the singularities couldn't be any of the known ones, and that somehow then led us to conclude that there is a new singularity, new gradient shrinking soliton. So we're somehow using Ricci flow to construct gradient shrinking soliton and not like the other way around, using gradient shrinking solitons to understand Ricci flow. Okay. Anyway, so let me get back to this result over here. So as I said, this result allows us to kind of find these regions that in some sense separate the part of the flow that becomes singular from the part of the flow that survives the singularity. And again, these are the regions where we want to perform a surgery. So for example, if we see a cylindrical region, then we would like to cut along the cylinder, just like in the 3-dimensional Ricci flow. We can do something similar for these kind of cylinders, these 2-dimensional cylinders. You have to think about it for a while, and it works too. And then for these conical regions, well, we see this kind of region that becomes very singular near the cone tip, and then we can somehow cut along the kind of cross-section of the cone and glue in something that's smooth, that kind of smoothens out the cone point. Okay? Okay, so this at least gives us some hope that there might be some kind of theory of Ricci flow with surgery in dimension 4. And this is just something that I just want to present as a conjecture. Okay, so this conjecture now says that essentially we should be able to do Ricci flow with surgery or Ricci flow through singularities in dimension 4. Okay, so what do I mean by this? So I mean that for any given initial condition, meaning a closed 4-dimensional Riemannian manifold, there should be some kind of singular Ricci flow starting from this initial condition. And so what is the singular Ricci flow? Well, it's basically kind of the types of objects that we've seen before, okay? So it should be some metric flow that allows a regular singularity composition. The initial time slice should be the given time slice. The singular part should have the dimensional bound that we've discussed before. Kind of most of the time slices should be mostly regular in the sense that most time slices are orbifolds, kind of that's the worst singularity most of the time. And we have some kind of, some kind of control how the topology changes as we pass a singular time, okay? So I could actually make this pretty precise, a pretty precise conjecture here if I just added maybe a few more sentences to this. And I'm pretty sure that this is kind of the thing that I'm pretty sure that we should expect something like this. Yeah, sorry.
And why, say, you asked that, the thermal point, you just asked for almost all this, so since the singularities that show up are only on orbifolds, so why you would allow worse things?
Oh yeah, so I mean, in some time slices you may see neck pinches, so you may see kind of these neck pinch singular times, but those are only like a set of measures 0 times. Yeah, but then sometimes you may see a conical singularity, like a cone like becoming singular, but then that cone may just become an orbifold conical point, and then I'm just going to keep the orbifold conical point forever, because I'm still counting this as regular. Yeah, yeah, thanks. Okay, so this conjecture, in my opinion, is somehow the most interesting question in Ricci flow right now. Okay, so and for me, it's just like an analytical problem right now. Okay, so it somehow is a good way of engaging with Ricci curvature, and it would also kind of show us that this kind of construction of Ricci flow with surgery in dimension 3 was not just a fluke that happened in dimension 3, but that there's maybe some deeper connection between Ricci curvature and topological change. Okay? So this is like on an analytical level. But of course, it's natural to ask if there are any topological applications of this flow. And here you have to be a bit careful. I don't think you can prove the smooth Poincaré conjecture or anything, but you have to somehow find conjectures that really fit kind of the information that's provided to you by the flow. Okay? So here's just 2 possible conjectures. So one conjecture I call the PSC conjecture. So this concerns topologically PSC manifolds, so manifolds that admit a positive scalar curvature metric. And so the conjecture is now that if we take a topological PSC4 manifold, then we kind of can reduce it to a collection of PSC4 orbifolds with finite fundamental group. And the original manifold arises from these orbifolds via Gromov-Lawson surgeries. Okay, so they preserve the PSC property. So this is kind of essentially an if and only if statement. So we can kind of reduce the study of these manifolds to the case where we have finite fundamental group. Okay, so this is of course not as spectacular as the Poincaré conjecture, but in dimension 4, there's very little known about 4D topology. So this would already be something.
You also expect that you can say something about the type of positive scalar curvature metrics that you get, so about the space?
Yeah, you could probably say a few more things, but it may end up saying like it's made out of building blocks which admit soliton metrics, and then that's probably you won't be able to say much more. But maybe there's a few more topological characterizations you can give. Yeah. Okay, and then this is now highly speculative, but would also be spectacular, is like a potential application, and again, this is very speculative, is this 11/8 conjecture, okay? So which makes which asserts a relation between second Betti number of a spin smooth manifold and its signature, okay? And so kind of the nice thing about this conjecture is that this is really about two invariants of a manifold that we know how they behave in the flow. So B2, if this conjecture is true, would keep decreasing, and the signature would always remain constant, okay? So this is very tempting to kind of have some hope here. Okay. Let's see, are there any questions?
Can I ask a question? I'm not sure if it's good to answer now, but you made this comment saying that when you want to find applications of a nice Ricci flow, you need to find a problem that gives you information that is suitable for Ricci flow. I was curious what heuristics.
Yeah, okay, no, this is a good point. So the big difference between this potential Ricci flow and dimension 3 Ricci flow is that in Perelman's Ricci flow, you would perform these surgeries, or you would kind of certain components would go extinct, and you kind of remove them, and you would fully know what their topology is. Here, what could happen is that you have components that become extinct, and they're just solitons. So we can't classify all solitons. So you have components that go extinct, but you don't really know, I mean, you know that you can continue the flow past those singularities, but you don't really know much about their topology. So that's why you can't really classify the topology of the initial manifold, but there are certain things that you know about the topology that you lose. So for example, you know that maybe second Betti number, you know they have finite fundamental group locally in some sense, and you know that they have zero signature and things like that. Yeah.
So in other words, you have applied to statements which are invariant under the topology of the solitons.
Yeah, or like which you know that the solitons obey. Yeah. Yeah, good point. Thanks.
Can you start from SP manifold and you have this procedure of surgery? Are the building blocks still spin? So
Yeah, they remain spin too. Yeah. You know, hypothetically, if this conjecture is true. Any other questions? All right, so now let me just pass to the last part of the talk, which is now work that I did joint with Eric Chen, who was at UC Berkeley for a few years, where we somehow now want to discuss the resolution of conical singularities, okay? So as you can see that this problem of constructing a Ricci flow with surgery in dimension 4 can be broken into smaller problems for every single type of singularity model, okay? So you have to somehow discuss how are you going to resolve cylindrical singularities of each type and how should you resolve conical singularities, okay? So in this project we wanted to study conical singularities because they're somehow the new kid on the block, okay? All right, so here's again the question. The question we started out with is, suppose you have a conical singularity, how can you flow past beyond the singularity, okay? So let's say the easiest case, suppose we have a precise cone, okay? So I'm going to write this cone as, just so we are on the same page, the cone metric I denote by gamma is equal to dr squared plus r squared times some metric on the link, okay? It's a 4-dimensional cone, and I'm going to assume it has positive scalar curvature. Everything here will have positive scalar curvature because that's somewhat natural to assume in the flow. Okay, so this thing here is the cone. And then I want to find this Ricci flow, which at time 0 is the cone, essentially. I don't know how to say this about the singularity, but roughly speaking, at time 0, the metric should be the cone. And then it should kind of smoothen out the cone. Okay? So if you look at single time slices, you're going to see something. Every time slice is kind of asymptotic to the cone, so its cone at infinity is the given cone, but it kind of smoothens out the vertex at kind of larger and larger scales. Okay? And then as the time t goes to 0, you're going to converge to the cone metric. Okay, okay, so a flow like this, in order to construct this, it's a quite subtle thing. Okay, so you could somehow say, why don't we just kind of smoothen out the cone point somehow and then evolve the flow? But kind of the important thing here is that we need to ensure that the flow that we construct doesn't become singular again, where the singularity is modeled on exactly the same cone. Okay, so we really need to kind of have some improvements, some kind of entropy increases and so on. And so it turns out that the only way that I see how to resolve the cone is to find a precise solution, and namely a solution that's self-similar. Okay, we call this an expanding soliton. Okay, so the solution here should just, all these time slices of the solution should just be homothetic to one another. Okay, so essentially what we now need to do then is we need to construct one single time slice, which is this expanding soliton, which we know where the flow evolves by rescaling, and we need to make that time slice asymptotic to that cone, so that if we kind of scale it down to scale 0, we're just going to converge to the asymptotic cone, and that's the given cone. Okay? Okay, so let me make this more precise. We're going to look at what we call expanding solitons. So these are metrics, Riemannian manifolds, equipped with a vector field that satisfy this kind of modification of the Einstein equation. Okay? So this basically says it wants to expand under the Ricci flow, and then we have this Lie derivative, which somehow allows the flow to evolve modulo diffeomorphisms. And then very often we're going to choose this vector field to be a gradient vector field, and in which case the Lie derivative becomes a Hessian, and we will call this soliton a gradient expanding soliton. Okay? So essentially what we're going to want to find is a gradient expanding soliton, or an expanding soliton, or gradient expanding soliton that's asymptotic to the given cone. Because then we can look at the associated Ricci flow, which is just the given metric pulled back by a family of diffeomorphisms that are kind of the flow generated by this vector field, and rescaled by the time factor. And this family of metrics will solve the Ricci flow equation. You can just verify this. And well, as time goes to 0, the metric, at least the isometry class of this metric, will just scale down and just converge to the cone at infinity, and that will give us, essentially the flow coming out of this cone. Okay. Are there any questions on this? Just to make sure we're on the same page in terms of the goal.
To perform surgery? Would this be enough to perform surgery?
Yeah, this would be enough. Yeah. So of course, I'm omitting some details, but like this way you can increase the entropy, and then you can. Okay.
There is some condition on H, right? So this will impose some condition on the G0 method that you on the singular core, right? The fact that you want to defigurize only using expanding soliton will pose some condition on the cone that you start with, right?
I'm going to run the flow, and maybe at some point I run into this cone. I don't know what this cone is. There's very little control I have on the cone. And then I want to find another Ricci flow starting from this cone.
Just knowing that this cone comes from a Ricci flow.
Yeah, actually I'm not even going to use that the cone comes from a Ricci flow. I just know that it has positive scalar curvature. That's the only thing, yeah. I doubt that we will be able to say much about what the geometry of the cone is based on it coming from a Ricci flow. But that's a good point. I thought about this for a long time, yeah. Okay, so now let me just show you this theorem that we proved first. So what we proved is the following. So suppose you take a smooth PSC cone metric, and the only thing that I require here of this cone metric is that the link has the topology being a spherical space form, okay? But other than this, it has to be positive scalar curvature, and any metric on the link is fine, okay? So no further conditions. Then given this cone metric, we prove that there is a PSC gradient expanding soliton on this kind of corresponding space, R4 mod gamma, that is asymptotic to the given cone, okay? So for every cone with positive scalar curvature and cross-section being a spherical space form, we can just find the corresponding kind of resolution, this corresponding expanding soliton. Okay, so this kind of fully answers this question in the topological case, in the case where the topology is, where the cross-section is S3 mod gamma. Okay. Any questions on the result? Okay, before I say a bit more about this result, let me just make a few remarks about the history of this problem. I mean, this type of problem, finding an expanding soliton for a given cone, has been studied before, for example, by Felix Schulze, Miles Simon, or Alex Deruel. And they found they had a different theory, but this theory was very much limited to the case where the cone metric has positive curvature operator. But that's something that we can't guarantee in the Ricci flow. So it's really crucial that we remove this extra condition, but it also meant that we had to find a different technique of constructing expanding solitons. The other comment is about what's the corresponding question for mean curvature flow? Well, expanding solitons in mean curvature flow are called self-expanders, and you could ask exactly the same question. And now for mean curvature flow, you're lucky because the expanding soliton equation for mean curvature flow just becomes a minimal surface equation for some kind of conformally changed metric. So in this case, you could somehow solve the equivalent result just by a minimization procedure. Okay? But unfortunately, no such analogy exists in Ricci flow, so you can't construct this soliton by a minimization procedure. So we really need a different technique to show this existence. And some of the only technique that somehow seems to be still available is called the degree theory. And so this is what I now want to explain on the next slide. Okay, any questions before I move on? Okay, so let me explain what I mean by the degree theory, and then we're going to form a notion called the expanded degree. Okay? And so let me start a bit from the beginning again. So I'm going to change my setup a bit because it will be a bit more convenient. So my setup will be, I'm going to fix a compact 4-manifold with boundary. I'm going to call this X. Okay, so you don't need to worry too much about it. You can always assume that X is just a 4-disk. Okay, so X is just roughly the topology of your expanding soliton plus the boundary at infinity. Okay, think about the 4-disk. That's somehow good enough for now. Okay, and now I'm going to look at the following map. I'm going to look at the map between the following two spaces. So the first space here, the domain of this map, consists of the set of all asymptotically conical gradient expanding solitons. Okay? So those solitons that I want to construct. And well, the codomain is the space of all cones. Okay? And the map just takes every expanding soliton that's asymptotic to a cone and maps it to exactly that cone. Okay? And so then the theorem just says that this map is surjective. So that's what we need to show. Okay? We need to show that this big map pi is surjective. Okay? And so now let's assume for a moment that we live in a world where these two spaces are finite dimensional smooth manifolds and compact. Okay? So then one way of showing that this map is surjective is by computing its degree. So if the degree is non-zero, then the map is surjective. Okay? But of course, that's not the case here. These are infinite dimensional spaces, and they're not even really, they don't even closely resemble a manifold, as we'll see in a moment. Okay? So nevertheless, what we showed in this paper is that this map pi indeed has a well-defined degree, and we call it the expanded degree. So the degree is an integer, and you can somehow compute the degree in the standard way. Okay? So you pick an element gamma here, okay? And then you're going to look at all its preimages, and then you're going to count up these preimages. So you're going to count up the number of expanding solitons that are asymptotic to a given cone, and you have to count with a sign depending on the index of a certain operator. So don't worry about this. Okay? So in particular, this then shows that if the degree is non-zero, then the map is surjective, and then we've shown our theorem. Okay? And then in a second result, we showed that the degree of this model here, the disk or its quotient, is equal to 1. Okay? And then you can put this together, and you get that the map is surjective. And you solve the question. All right. Okay, so I should just say that this is not the first time people use degree results in analysis. They are kind of very standard approaches. So for example, degree theories were used by, at least in geometry, by Trommer and White for minimal two disks, Anderson, Chang, and Gabe for asymptotically hyperbolic Einstein metrics, and then Bernstein and Wang in the mean curvature case, in the mean curvature flow case. But what makes this case special here is that many of somehow the ingredients of these theories, they break down in the Ricci flow case. So we have to find different ways to solve a few problems that show up. And I'll show you in a second. Okay, let me see. Are there any questions on this approach? All right, I'm going to give you a few more details on this theory in a moment. But let me first just give you a bit of an outlook, what we want to do with this new kind of theory. Okay. So of course, now we've constructed expanding solitons for if the link of your cone is a spherical space form. But we want to construct expanding solitons for all cones because we want to resolve all conical singularities. Okay, and luckily, these all have positive scalar curvature. So the links have positive scalar curvature. And so therefore, we know what the topology of the link can be. Okay? So the link has to be a connected sum of spherical space forms and copies of S2 cross S1. Okay? So, this is not, at least we have some description of the topology of the link. And so now we want to find, for each of these topologies, we would like to find an expanding soliton asymptotic to a cone with this link. Okay? And so we first have to find a topology on which these expanding solitons are defined. And there's a very clear candidate if you think about this. So basically, you're going to replace every single spherical space form with the corresponding disk quotient, and then kind of these S2 cross S1 factors with D3 cross S1. Okay, so there's a candidate for kind of the space on which the kind of expanding solitons are defined, or they're defined on the interior of the space. Okay. And so now our conjecture is that the expanded degree of these topological spaces is non-zero. So I think it's going to be 1. Okay. So there are some reasons to believe that that's true.
Why D3 crosses 1, not D2 cross?
That's a good point. Yeah, this is actually the only thing that's not super clear, but we want the second Betti number to drop, so we don't want to increase it. And in fact, a student of mine just analyzed the case of D2 cross. What is it? S2? Yeah. And so he found that the degree of that is 0. So it really kind of confirms that we shouldn't look at this one. We can probably show that the expanded degree of this topology is 1, but it's still a work in progress. Okay.
So that's like looking at a whole bunch kind of singularity kind of resolution. That's the last.
Which one?
It's like you do a whole bunch. You add a whole bunch to
The hole punch? Yeah, I think that corresponds. Yeah, it is essentially a hole punch, but for cones instead of for cylinders. Yeah, yeah. Any other questions?
Is there an issue with, like, if you have a disconnected link?
If you have a disconnected link, then you just look at every single cone on its own. It could be disconnected. Yeah, I mean, this is unclear whether they're shrinking solitons with more than one end. But yeah, then you just look at every single end on its own. But yeah, good point. Yeah. Okay, again, this is just a conjecture, but there are certain kind of heuristics to believe why this conjecture is true. Okay. And so if we could solve this conjecture, then this would imply the existence of expanding solitons asymptotic to every given cone with positive scalar curvature. And that would be exactly the ingredient that we needed to kind of flow through conical singularities. Okay? So to illustrate this, let me just state what I call a 90% theorem. So it's 90% because I haven't written it down, and it's a lot of technical details, so I don't want to make a precise statement, but it also doesn't make sense to write it down right now, but let me just, as illustrative purposes, to say what I expect. I expect that if this conjecture is true, then we can essentially find a Ricci flow through singularities, or a singular Ricci flow, as long as we're only flowing through conical singularities. Okay? So the statement, just as a motivation, would be something like this. It would somehow say that there exists a singular Ricci flow through singularities up until some maximal time t. And if t is finite, then at this time we have one of those two cylindrical singularities. Okay? Okay, so essentially, if we get stuck, then we're not getting stuck because of a conical singularity. We get stuck because of these other singularities, and then kind of, maybe you want to do some work on these conical cylindrical singularities, and you can remove another condition and so on. Okay, but this should be possible. Okay. Any questions? All right. So now let me just give a few more details about this expanded degree, and I'm sorry if this is getting a bit more analytical, but let me just give you a few things that show you a few ingredients that go into this theory. Okay. So again, I want to define this expanded degree, and I want to somehow explain how to do this, carry this out on a technical level. Okay, because there are some interesting geometry that happens here. Okay. So again, what we're going to look at is this map that assigns to every gradient expanding soliton its asymptotic cone. Okay. So let me just call this space here M grad, the space of gradient expanding solitons, asymptotic to cones, and then this is the space of cones with the corresponding cross section. Okay, so this is just a quicker way of writing things. And so now here's the problem. So we would like to find a degree theory, and if you just follow the standard steps of finding a degree theory that are used in all these other theories, then the problem that we encounter is that the domain here is actually not a Banach manifold. It actually is only kind of locally, looks like a kind of a infinite dimensional like subvariety, analytical subvariety. So it's a potentially singular space. Okay, and this creates problems if we want to define the degree, for obvious reasons. Okay, so this is kind of not the right setup. And so now the way how we can resolve this issue is by extending the map onto a larger domain, and also by extending the codomain further. Okay, and so this has a nice geometric interpretation. So what we're going to do first, let me first describe how we're going to extend the map, the codomain here. So now instead of looking at the space of cones, I'm going to look at the space of what we call generalized cones. Okay, so a generalized cone is a space that's invariant under dilation. Okay, but in a cone, dilation happens along geodesics. Okay, but in a generalized cones, dilation doesn't have to happen along geodesics anymore. So if you write this down in Riemannian geometry, a cone metric looks like dr squared plus r squared times the link metric, but now I allow this cross term for some one form in here. Okay, so these are kind of more complicated dilationally invariant metrics. Okay, so I'm going to replace the space on the right with generalized cones. Okay, I'm going to call these generalized cones.
So philosophically, I mean, for example, when you're looking at shrinkers, the conical structure comes from equality case and some functional, right?
Yeah.
The fact that you're doing this here, that's because, there are expander entities, but they're not somehow useful or relevant or applicable.
Yeah, and I mean, we're only going to look at some small deformations of cones in the direction of generalized cones. It's not like, it's not that much of a geometric significance, but yeah. Does that answer your question? Yeah. You'll see in a second maybe. So then, and then on the left-hand side, we're going to now enlarge our space to include not necessarily gradient expanding solitons. So we're going to remove kind of the gradient here. We're going to look at all expanding solitons. And so there's a kind of a clear relation between between something being a cone and kind of the radial function to be the radial vector field being a gradient vector field. That's maybe the kind of the issue here. Okay, and so we'll see that there's some kind of duality between something being a cone and something being and then the corresponding expanding soliton being gradient. Okay. Okay, let me not get into this. It's not very clear. It doesn't go both ways. Okay. All right. So let me just now draw a picture, and I'm just briefly explain kind of how this theory is, how we're going to approach this theory. And I'm sorry if this is getting a bit more analytical. Okay. So let me just look at this picture over here. So here I'm trying to draw the space of all generalized cones. Let's assume it's two-dimensional. And within the space, there is the space of cones. It's this green line. Okay. So I've extended the green line, and I'm really just looking at small extensions away from that green line. Okay. Okay, so I want to find a pre-image of this map pi over the green line. And then up here, this is now the space of all expanding solitons, not necessarily gradient expanding solitons. So the pre-image of the green line consists of this line and this line. These are all expanding solitons that are asymptotic to cones. And then within this pre-image, there is this kind of green region, which are the expanding solitons that are gradient. Okay? So I want to find a pre-image of every green point here within that green set. I don't care about this stuff up here. Okay? Okay, is that setup clear? So, all right, so now the issue here is, so now here let me just say a few ingredients. So first of all, we can show that there's a neighborhood of the set of gradient expanding solitons, which is actually a Banach manifold, just some open neighborhood. Okay, so weirdly, we can somehow say that the space here is a Banach manifold. Okay? So we have a Banach manifold structure here, and this kind of allows us to talk about degree theories to a certain extent. We can also show that the map, if you restrict it to the gradient expanding solitons, so if it's restricted to the green line, is a proper map. That's another important ingredient for degree theory. And now there's this issue that, I don't know, should we count the pre-images only in this green part or the pre-images in the black part? Okay, in this black part, these are the expanding solitons that may not be gradient, and we may not have a Banach manifold structure here. So we actually want to ignore these points here. Okay, but what if they're somehow connected in some way? And so now kind of so the issue here, as I said, is there might be components in the pre-image of the set of cones that are not gradient, but luckily it turns out that these are different connected components, so we can completely ignore them. You will never be able to walk from this black region into the green region. And this is somehow which will now then make this degree theory possible. So we can then define, and you can ignore the text, you can then define you can kind of decrease this open neighborhood here in such a way that the open neighborhood does not include this black line. Okay? So that we're kind of only looking in a neighborhood of gradient expanding solitons, and if we're moving away from this, then it also corresponds to deforming the cone in a direction where it's not a cone anymore. Okay? And so now we can put these theories together, and these theories really allow us to come up with a degree theory. So over every point here, we can define a degree which is locally constant in the space of cones. And then the last ingredient is the image, the space of cones, is path connected. Okay, and so this follows by a result of Marquez, or then Bruce Kleiner and myself, where we show that the space of positive scalar curvature metrics is connected. Okay, and so since then the space of cones is connected, we get that the degree is everywhere the same. And so the degree is somewhat globally defined. It doesn't depend on the specific cone. Okay, I think, I'll stop here. Thanks for your attention.